Hello, and welcome to another webinar in the Industrial Heating Equipment Association series on sustainability and decarbonization. My name is Kelly LeCount, and on behalf of IHEA, we want to thank you for joining us today. In addition to the webinar series, IHEA hosted the first Industrial Heating Decarbonization Summit this past October. The event brought manufacturing business professionals together to learn about efficient technologies and to discuss challenges around the changes in industrial energy supply, energy management, and carbon emissions. Feedback from the event was incredibly positive, and IHEA is pleased to announce the 2025 summit will be held September 29th through October 1st in Indianapolis, Indiana. Watch for further details on IHEA's website. Before we get started, I would like to remind everyone that all attendees are on mute. If you have any questions along the way, please type them in the Q&A panel. The speaker will address questions at the end of the presentation. All attendees will receive a brief survey after the webinar via email. It will take just a few moments to reply. We appreciate your feedback as IHEA continues this critical initiative for the industrial heat processing industry. One last announcement, this webinar is being recorded and will be available under the Sustainability tab of the IHEA website within the next few days. All registered attendees will receive an email once the link is available. Now I'd like to introduce the presenter for today's webinar titled Understanding Carbon Footprint and Costs of Atmosphere versus Vacuum Processing. Brian Stern is a product development manager at Gasberry Thermal Processing Systems. He has been involved in the development of vacuum furnace systems for the past 8 years and is passionate about technical education and bringing value to end users. Brian has a BS in Mechanical Engineering from Georgia Institute of Technology and a BA in Natural Science from Covenant College. In addition to being a member of ASM, ASME, and a former committee member for NFPA, Brian is a graduate of the Metal Treating Institute's YES program and is proud to have been included in Heat Treat Today's 40 Under 40 class of 2020. Brian, thank you so much for taking time with us today. It's all yours.
Thank you, Kelly. I appreciate the introduction, and thanks everyone for jumping on today. We really appreciate your time and appreciate the efforts of IHEA in getting some of this information out there, both at the summit and through this ongoing webinar series. So we hope that you're able to get some value out of this topic. I know that going through it and preparing the information, we learned a lot along the way. So we're excited for an opportunity to share some of that value and bring it to you. So we'll jump right in. Most of the time they say to start a presentation by talking about what we're going to go over, but I want to start out by talking about some of the things that we're not going to be covering. What we aren't going to do is explain why this topic should matter to you. We're going to be talking about a number of things, both the energy consumption side, cost, and emissions. You might be here for one of those topics, all of them, and for different reasons, whether it's internally driven corporate initiatives, some legislation through a customer or vendor that's impacting you, but those reasons are going to vary for everyone. So we're not going to spend a lot of time talking about the backdrop of environmental policy that's bringing attention to this. This presentation is really going to be focused on this case study and the data that comes out of it. We're also not going to be going in depth into the calculation methods and calculations. Try not to get too far into the weeds with that. So if you're interested in some of the methods behind carbon accounting, I know IHEA has put a couple other webinars out there that have been great resources, even for me in preparing this. But it's not going to be as much a tutorial, again, as looking at the results and some of the takeaways and outcomes that we can learn from that. And finally, we're not going to be pushing what equipment you should buy here. This is not an agenda-driven discussion. Fortunate enough, working at Gasberry, we offer both kinds of equipment, and we saw that as a unique opportunity to be able to do a kind of unbiased review and just gain a better understanding of how these different approaches to heat treating do stack up. So we're excited to bring that to you. So what we are going to cover is a case study comparison between a natural gas-fired atmosphere IQ furnace and an electric vacuum oil quench furnace running the same process. We're trying to stack these furnaces up. If they're doing the same thing, how do they compare across their energy and utility consumption, the cost of actually operating that equipment, and the equivalent CO2 carbon emissions from running that process. So after we go through those results, we'll look at some of the key variables that can change what that picture looks like. And then we'll summarize the key takeaways that we can learn from this exercise. And ultimately, the objective here is to just equip you with information to gain some familiarity with things to look at when comparing and considering. One thing that will be outside the scope of this is some of the other reasons that you might choose between these two types of equipment. I'm biased. My background is in vacuum. I think there's a lot of advantages of that approach to processing, but we're not looking at process reasons that you might change it. There's a lot of other reasons to decide between those technologies, whether it's environmental, just the work environment that each of those pieces of equipment create, safety, process flexibility, insurability. Those are all important considerations, but we're really focused on just the nuts and bolts of how do these actually stack up from a carbon standpoint and a cost standpoint. So to look at that, we're going to be going through some background, looking at the pieces of equipment, the furnaces themselves, the workload that we're running, and the process that we're running it through. We'll do a brief overview of the calculation methodology, and then dive into comparing some of the results that come out across those three C categories: consumption, cost, and carbon emissions. We'll look at those key drivers and then go over some of the takeaways. So going through the background first, we'll start out with the furnaces. We've got the atmosphere IQ furnace on the left here and the vacuum oil quench on the right. Each of these pieces of equipment has the same size work zone. We're looking at a 36, 48 work zone size. One of the primary differences between these pieces of equipment is that the atmosphere IQ uses recuperated gas-fired burners for its heat source, where the vacuum furnace uses electric elements fired by transformers with SCR controls. A couple other notable differences between the pieces of equipment are that the IQ furnace has 12 inches of ceramic insulation, where the vacuum furnace only has 2 inches of graphite felt, and that's pretty typical for vacuum construction, just in an effort to maintain the process environment purity, as well as keep pump down time to a minimum. So in an effort to maintain that environment, the atmosphere furnace uses endothermic gas. This particular furnace was measured at 750 CFH for its process environment, where the vacuum furnace removes the atmosphere to create that protective environment. So two different methods for creating the process environment, and we'll see that both that insulation difference and that atmosphere difference are some of the key things that impact the outcome here. There are a few other differences, things like total load capacity, but because we'll be processing the same workload in each, those kind of cancel out. And again, the objective here is an apples to apples comparison of two similar sized pieces of equipment processing the same load. So speaking of the workload and process, we'll be looking at just a really basic neutral hardening process with 2,500 pounds of 4140 alloy steel, a simple ramp soak profile with about an hour and 45 minutes to ramp, which corresponds to about a 15 degree per minute ramp rate, soaking for 2 hours at 1550. And just accounting for each of the different components of that workload, the work itself, grids, baskets, and liners, pretty typical picture of what a workload might look like going into this furnace. And I know we said we won't get into the details of the calculation, but wanted to do just a brief overview. Here we have an information flow diagram kind of outlining the process that was used here. We're taking that information about the workload fixturing, as well as the cycle definition, how long we're holding it, the temperatures, et cetera, and combining that with measured and calculated operating and performance data for the furnace, feeding all of that into a model for the furnace to come up with energy and utility consumption. And when we have that consumption value, we can combine it with prices for those utilities to come up with operating costs per cycle or on an annual basis. And we can combine that same energy and utility consumption with emissions factors to come up with the carbon emissions. So you can see that that energy consumption will drive and is related to the operating costs and carbon emissions, which we will see. So I know we might be coming from various backgrounds of just exposure to the emissions conversation and emission things like emission scopes. So I did want to take a minute to kind of go through some basic terminology and an overview of that. There's, I'd say, a fairly common misconception that if you remove on-site combustion and move to electrification, that you eliminate carbon emissions. And that might be true if you're specifically contracting for renewable sources of energy. But in general, for carbon accounting, you're going to be required to account for all sources of emission associated with that process. And that'll include things like on-site combustion, the CO2 generated there, which would fall under scope 1. But it also includes the emissions associated with any electrical or energy generation used to generate the power that's used in your process, which falls under scope 2, I'm sorry. And it also covers any of the emissions associated with things like transportation of product, use of product, downstream. So in our case, often with thermal processing equipment, we're looking at things like processed gas, generation, production, delivery, things like that. So the good news is that it's fairly simple to account for the emissions associated with those things because in most cases, emissions factors allow for direct conversion from amounts of energy consumed to equivalent CO2 emissions. And those emissions factors are publicized and made available at a regional level, at a national level. So you can look up those values and find them published by the EIA and the EPA. So some of those will be fixed, such as the values for electrical generation. But like we mentioned, with some of the consumption emissions associated with scope 3, it's going to vary depending on the region, depending on your infrastructure. And a really important thing to note here is that this will show up as we're looking at just electrical costs. But in general, when we're looking at electrical heating and electrical generation, there are many more processes associated with that than on-site combustion. You're taking some chemical fuel source and converting that into thermal energy, then mechanical energy, using that in generators to generate electricity, and then transmitting that electricity where you're bringing it back and then converting it back into thermal energy. Whereas for on-site combustion heating, you're going directly from chemical to thermal, and only dealing with the efficiency of conversion for that one process. So it tends to be very efficient. And just to illustrate that, we are showing here in this case study, we're using recuperative burners for that process at about 1550. So if you look at the efficiency associated with that burner, we're looking at something a little over 75% efficiency. And if you look at typical efficiencies for electrical generation associated with the different types of power plants, you can see pretty quickly that typical efficiencies in a burner are more efficient than your most efficient power plant. So unless you're using renewables, it's not necessarily a better option even for emissions. But that being said, looking at this plot on the right, you can see that renewables are growing significantly in their contribution to the grid, a trend that is expected to continue. And the more renewables that are contributing to the overall power generation in a given area, the better the electrical prospect is going to be. So we'll jump right into the results that came out of this model. This is a high-level overview of the results, and there's a fair amount to process here, but there's a few key takeaways that are kind of surprising, and we'll unpack those a little bit. So just to orient to the page here, we've got each furnace, atmosphere, and batch vacuum with each of the categories of contribution summing up to a total for total energy consumption, cost of running a single batch, and the emissions associated with that single batch. So right off the bat, looking at energy consumption, we can see that the atmosphere IQ is consuming 2,300 to 2,400 MBTU per cycle, whereas the vacuum furnace is only consuming about 1,450. So we're looking at a significant increase in energy for the atmosphere IQ, about 60%. But despite consuming almost 60% more energy than the vacuum, the atmosphere IQ is cheaper. And importantly, we can see that the emissions are higher, and that's coming from that dynamic of just the electrical utility being significantly more expensive. So despite consuming more energy, the atmosphere IQ is cheaper to operate primarily because of the fuel source. And we're looking at about a 20% increase in emissions associated with that electrical utility. And we'll dive into a breakdown, some more of the details that are driving those results in the next few slides. So I put this slide together just to illustrate how many different things are coming into play in this model. You can see there's a lot going on. There's a lot of pie slices here. It's really busy. So in an effort to simplify that, we combine some of the categories. You can see things like the work thermal storage from the grid, furnace thermal storage, all combined into thermal storage losses. And similar things are done with steady state holding losses through insulation, et cetera, just to collect some of those categories and simplify the information we're looking at. And this particular pie chart is for the atmosphere IQ energy consumption, but we applied a similar process to all three of those categories for both furnaces. So starting off with energy, again, we've seen the overall result here, but diving into some of the pieces that make that up. The first thing we can notice is that the thermal storage losses are a similar value for each furnace. They show up as different percentages because they're a different portion of different totals, but essentially the storage losses for each furnace are equivalent because we're running the same workload. We're heating up the same mass, same material to the same temperature and cooling it down. So while that's equal, we're still looking for where is this difference primarily getting driven from. And if you're like me, one of the first things that you think of when it comes to furnace equipment energy consumption, one of the first things that you're thinking about is the insulation losses for actually holding the equipment at temperature. And we can see here that the atmosphere IQ is about a 5% contribution from the insulation losses, whereas the vacuum furnace is 30%. So it's a much, much higher insulation loss. And that goes back to that difference in insulation construction that we noted earlier, and some of the advantages of having higher insulation. But the question is if the atmosphere furnace is consuming so much less from insulation than the vacuum furnace, why is the total higher? And I think this is one of the most eye-opening pieces of this exercise for me as we were looking into it. We have a little bit of contribution from things like the pilot exhaust and flame curtain and burner flue losses, but at 12 and 10%, that doesn't account for this significant difference in the total. But if we look at the endothermic gas between the actual gas used for the process, the endo generator burner, and the electric auxiliaries that it takes to run that equipment, looking at 42% of the energy associated with the atmosphere IQ is coming just from the process gas. So the main takeaway there is that even though the vacuum furnace is less thermally efficient, it's only using 11% of its consumption is going toward creating the atmosphere. So it's much, much more efficient at generating the atmosphere, the protective atmosphere that's used for its processing. So next we'll jump into the cost portion of this. And something I want to note with that is that the values don't change significantly in the breakdown. And pointing back to that workflow diagram, we know that both the cost and the emissions are going to be driven from the energy. So the main difference that we see in jumping from energy to cost is that anything that's electrical is going to get inflated in both the cost and emissions. And that can be pretty clearly seen as we're seeing these electric auxiliaries, which here made up 9%. That pie slice just inflates right up to 20%. So that's the main difference that we're going to see in both the cost and emissions, again, with the batch vacuum being more expensive to operate, but the breakdown of contribution for those reasons being essentially the same, with electrical sources being exaggerated a little bit more. So similar breakdown here, with the primary components being the thermal storage losses in the batch vacuum. So the amount of energy used to heat and cool the furnace and the workload, with the endothermic gas being the primary contributor for the atmosphere IQ. And still seeing that slight increase in the overall value for the batch vacuum, but the emissions are very close, or much closer than the other categories. So we'll jump into talking about some of the variables that are driving those results. There's a lot on this slide, and don't worry, I'm not going to go through it all. We've already talked about some of the things here. This is just to illustrate how many different variables are going into this model that can potentially change the outcome. So some of those things are really intuitive. If you were to change the insulating value of the insulation pack, that's going to have a change, either positive or negative. You could change the workload size of the material. If the workload gets larger, those storage losses are going to increase. So there's a lot of things that can change the model. And what we're really interested in is what things change the model the most. So with this model at our disposal, we were able to kind of do a sensitivity analysis to look at what things have the greatest impact on the results and consequently really deserve our attention as we're looking at equipment and speccing equipment for a particular process. And several of those variables really rose to the surface. So we have 7 listed here, and we'll have an opportunity to go through, I think, just about every one of those. Looking at burner tuning and efficiency, electrical element conversion, the endothermic gas generation associated with the IQ, cooling water sourcing, nitrogen infrastructure setup and supply, geographic location, and the furnace configuration. So jumping right into burner tuning and efficiency, this is one that's very often talked about. This applies just to the IQ. I mentioned earlier that we're looking at recuperated style burners in that furnace. So we're looking at 75% efficiency for that. But that efficiency is dependent on your actual burner configuration and design, but additionally, it's impacted by things like your control scheme, what your turn down ratios, how efficient that burner is at operating in a turn down state, as well as just your air to fuel ratio, and how close you're able to operate that burner to ideal conditions. So if we were to change that, instead of operating at 75% efficiency, which is where that burner should be, very often we'll see in installations things like burners not tuned properly or missized and operating at a poor turn down condition. And if we were to change that efficiency to 50%, which I'd say is pretty modest for the kinds of values you end up seeing in the field a lot of times, that's going to increase the overall energy consumption of this process by 21%. And that's leading to a 16% increase in operating cost and an 18% increase in the carbon emissions. So a simple thing like burner tuning can have a dramatically detrimental impact across all three of these categories. So it's really important to pay attention to the tuning on your burners. Next up, we have the electrical element conversion. This tweak is looking at what if you were to take that IQ furnace and convert it to use electrical elements instead of burners. This is, I think, a pretty popular target because the electrification is just generally understood to be a positive thing from an emissions and operating cost standpoint. And if you look, we do see initially a decrease in the amount of energy consumed. And that's primarily coming from the fact that we lose the burner flue losses, which are an energy loss that's kind of inevitable with burner operation, that you're going to be throwing some energy away through the hot gas stream that's coming out of your burner. But we see a 52% increase in the operating cost and a 20% increase in the carbon emissions. And again, in general, that's just coming from that efficiency of supply using electricity for thermal energy because of the number of conversions that you have to go through from the primary fuel source to the end use. And when you're turning it into just thermal energy and heat, it can be more efficient to just do that on site, with renewables being the exception, and that growth of renewables being something that we have to keep in mind. But this is just to illustrate that if you were to just, without any other information, go in and do a conversion with the objective of reducing emissions, that may actually be counterproductive to what you're trying to do. Next, we have the endothermic gas generation. This is again looking at the IQ and comparing it to the baseline that we had in the case study. For the case study, we were looking at that endo generator as being what we would call right-sized or sized appropriately for the 750 CFH. However, something that we'll often see in the field is endo generators being oversized for the amount that the equipment is actually consuming or is required for the process. And some of that can come from not knowing how much is going to be consumed until the process is fully vetted and developed. But oftentimes, if a generator is oversized, the amount of gas that is required will be consumed, but any excess, rather than turning down the equipment, because it can be more expensive to have a control scheme or burner design that allows for that equipment to be burned down. And because the source gas is relatively inexpensive, you can just burn off the excess gas, create more than you need, and just essentially throw away the rest of it. So if we were to take that right-sized generator and replace it with a 1500 CFH generator, and operate the equipment with that, still consuming the same amount that we needed, but burning the rest away, we're going to see that 52% increase in energy consumption, 38% increase in operating costs, and a 45% increase in the carbon emissions. And just point out again that these are not increases of just the endothermic portions. These are increases across the entire cycle cost. So they're having that one pie slice, and the change to this variable is having enough impact to change by these percentages. So another really significant thing to be paying attention to is how you're generating your gas, what you're doing with it if there's excess, and what your turn down scheme is for that equipment. Next up, we have the cooling water system, and this one's just huge. In our case study, we're looking at just recirculating in a closed loop for the cooling water. But a lot of times we will see people operating thermal processing equipment where in order to get the cooling water, they're just plugging into a city water connection, flowing it over the equipment, and then just dumping it down the drain. And that does save on the upfront capital cost. You don't have to purchase the water skid. We do see a decrease in energy consumption. And diving into the model, this is coming from the fact that you're no longer running that recirculating pump for your recirculating system. So there is a little bit of an energy savings there. You're not running that pump all the time, but it leads to an operating cost increase of 174%. So it's just astronomically expensive. And if you look into the ROI for closed loop cooling systems, they pay for themselves very quickly. This is not something you want to be doing. There's a 30% increase in the carbon emissions associated with all the processes used for the purification of that water. So taking it and just dumping it down the drain is something that you really want to be avoiding, because there's a significant cost associated with doing that. And then we have the nitrogen sourcing. I mentioned back on the emissions terminology slide that there are some emissions factors that are more or less fixed based on the region you're in and the sources and your local supply grid. For things like electricity, that's a value you can just look up. It's similar for water. But when it comes to nitrogen sourcing, or really any process gas sourcing, there's a number of different ways that this can be accomplished. You can have cryogenic liquid delivered, you can have compressed gas delivered, or there's options for on-site generation. And each one of those options is going to have a different footprint when it comes to the carbon emissions that are associated with it, as well as different cost. So in our model, this was making some assumptions because this type of emissions factor is so situational and specific to a given context. So you can see there's things like having to assume what's the round trip delivery from your site, to and from your gas supplier. Those kinds of things will impact this. For our model, we were looking at compressed gas as kind of a worst case with the highest amount of CO2 equivalent generation per volume. But you can see that number varies pretty widely, with the lowest number being associated with on-site generation, because you get rid of all those transportation costs. But this doesn't capture that on the cost side, you have a significant upfront capital expense to be able to get into this situation where you have a lower emissions associated with your gas. So this really points to the fact that depending on what your objectives are with cost, what that lower emissions is worth to you in terms of ROI on the equipment, looking at these different options as far as things that are situationally specific to your particular facility and context does have a significant impact. And that brings us to location, which impacts some of those variables. But this is one that might have been on your mind as we were going through this. All the numbers that we've talked about so far, we're using US average rates. So just across a US average, what are the emissions factors for utility generation? But that doesn't account for the fact that this is location specific. So what we want to do to illustrate that is kind of take this case study, and we're going to take it from US average numbers, and we're going to bounce it around to several different states and see how that impacts the operating cost, the relative operating cost between the two pieces of equipment, and the relative carbon emissions. And keep in mind that the energy consumption is not going to change. The amount of energy required to heat that workload in the furnace and run that process is going to be the same no matter where we're located. But what's going to change is what that costs to do, and based on the local contributions to the electrical grid, what that means for the relative carbon emissions. So pay special attention as I click through these following states to the ways that the relative changes between the green bars and blue bars. So we'll jump through from US average to West Virginia, Michigan, Texas, California, Delaware, Oklahoma, and Vermont. And you can see that just by virtue of where it's located, the picture can change completely. It can be flipped on its head, where here in a different location, the vacuum option has significantly lower emissions as a solution as a consequence of just the electrical generation makeup in that area. So location is something that means that we can't just generalize the answer to this question. You can't say this technology is in all situations better than the other. It really depends on your context, and that's something that has to be considered and looked at as you're making decisions around these types of equipment. And the final thing that we'll look at here is just the actual equipment configuration. I think this is something that's very often overlooked, so often overlooked that I overlooked it in the course of putting together this presentation, because we're looking to make an apples to apples comparison, and the two pieces of equipment that we're comparing in the case study we looked at are this Atmosphere IQ and this batch vacuum. But the Atmosphere IQ has the capability of loading a new load under the quenching load, which essentially creates a continuous flow that's just loaded and unloaded out the same side of the furnace. That boosts the index rate and the utilization for the furnace compared to the batch vacuum, where you have the additional pump down time. And without that loading over oil capability, our index rate is actually increased, so we're not getting loads out as quickly. Our utilization is lower, and it's not a great comparison compared to if we were to take that same piece of equipment and turn it into a continuous configuration, which just takes, it's essentially the same equipment, but the work flows through it. Very little capital cost. It's just adding an extra door, and you have to have the space in your facility to be able to handle unloading on the opposite end of the furnace. But in this configuration, the throughput for the furnace and the actual productivity of the furnace is a much better apples to apples comparison with the Atmosphere equipment. And if you do that, then you see a 9% decrease in the consumption from the baseline that we looked at, as well as a 4% decrease in emissions There's a slight increase in cost, and that kind of surprised me when I saw it. So diving again into the model, that's coming from an additional nitrogen backfill that's required for the unloading of the continuous configuration. But if we were to carry that same thought forward and just add another heat zone, then we'd see the index rate, the rate that we're actually able to move work from position to position, decreases by 44%. So we see a 66% increase in the utilization of the equipment and the throughput capacity. And across all categories, consumption, cost, and emissions, we see notable decreases. So you have to consider the configuration of the equipment when making a comparison. It's not just atmosphere, fuel-fired burners versus electrical equipment. Per load, the configuration of the equipment, whether it's single chamber batch, multi-chamber batch, or continuous equipment, it can have a substantial impact on both the cost and emissions associated with a given load. So there's a lot of advantages to be had, and this is one of the reasons that we're seeing a lot more push in the industry for some of these alternative configurations because of the benefits that they have. If we move our focus past just upfront capital costs to actually looking at what does it cost to operate this equipment long term and what are the efficiencies associated with it. So that was a fire hose of information, and just to try to kind of button it up here at the end, we'll go through some of those takeaways. A big takeaway that we have is that gas-fired atmosphere furnaces will typically consume more energy, and that's just intrinsically because both the atmosphere that they're using to operate, as well as the fact that burners have losses that electrical heating doesn't, where you just have a totally enclosed process without flue losses or concern for tuning the gas so you're not throwing energy away in that way. That being said, electrification does not always reduce cost and emissions. And that's important. It certainly does at times. It has a lot to do with your energy sourcing, things that we've talked about, like location, but it's not a safe generalization to just say that moving my combustion fire process to electrification is going to be beneficial from a cost or emission standpoint. You have to look more at the specific context to make that call. Growth in the renewable energy sector is a trend that will continue, and the more contribution there is from that sector, the better those emissions factors get, the more it pushes for electrification. And that will happen at different rates in various regions, depending on the infrastructure that's put in place. Some of the key drivers that we looked at that impact the outcomes are the equipment design and operation, what we're doing with it, how long we're holding, what temperatures we're running at, what we're putting through it. All of those things make a difference, as well as the utility infrastructure, things like how far we are from suppliers delivering gases, those transportation costs, and finally, location is just huge. These decisions cannot be considered in a vacuum, no pun intended, but they have to be made with an awareness of the context of location. You can't divorce it from that. And then finally, that multi-chamber continuous furnace configurations offer benefits that can flip these results on their head. If you change the way that a piece of equipment operates, it can lead to a totally different picture, and there's a lot of advantages that can come from doing that. So it's something that I think a lot of manufacturers and suppliers are looking at increasingly to be able to take advantage of some of those configuration benefits. Finally, work with your OEMs to determine your best solution. There's a lot to consider here, and speaking from the OEM side, it's certainly helpful to have early partnership over making decisions in which direction to go, so that you can get access to things like utility consumption for the different styles of equipment that you're looking at, and marry that together with your particular utility costs and emissions factors in your area looking at your specific context. Two parties have two different pieces of information that are required to make that whole picture. So definitely talk with your OEMs early to dive into that equipment. Got a page with just some of the appendix resources used here. So if you're interested, there's links for where published emissions factors can be found. And that's all I have. So if we have any questions, I'll turn it over to you, Kelly.
Thanks so much, Brian. That's a lot of great information, but yes, it was definitely a lot. So, yeah, we do have a question here. So, you were talking a lot about location. What led you to pick the states you did for the comparison, and how often or where are the results different?
Yeah, that's a question I've gotten before because some of the states are not what we would say are heat treat hubs across the country. Vermont is not known for its robust heat treat industry. Those states were chosen really because they represented the most dramatic shifts. So if some more obvious states, I'll say, were not included, it's likely because they were pretty close to the US average and there wasn't any dramatic shift in those graphs. So the states that were in there were really selected because they represented the most extreme juxtapositions of the relative emissions from electricity versus gas and the relative cost between electricity and gas. So trying to look at the most dramatic swings we could have, and anything else that wasn't included there falls somewhere in between.
Okay. All right, another question here. Drew's asking, were the differences for the continuous vacuum compared to the batch or atmospheric case?
Could you repeat that question?
Yeah, were the differences for the continuous vacuum compared to the batch
Okay.
or the atmospheric case?
They were compared to the batch. So the relative, I could jump back in that slide, but the slide comparing the different configurations, there were percentage changes. Those were percentage changes compared to the single chamber batch baseline, not relative to the atmosphere case.
All right. If anyone else has questions here, okay, we're getting another one. From your business perspective, do you see an uptake on more vacuum furnaces based on a need to reduce greenhouse gas emissions?
So I see that primarily getting driven right now by process considerations. And I'd go so far as to say I think a lot of the things driving vacuum are bigger than this from a process safety standpoint. I know insurance has become an increasingly relevant concern just with safety of the work environment and the work environment it creates. So outside of just generally considering electrification better, I think when it is driven by this, oftentimes right now, that may not actually be beneficial for emissions. But that being said, I think it will be soon. And I think it's a worthwhile investment for the future. And there's even cases right now where it is. We looked at that average, but I can say from just going through some of those variables with location as an example, there's about 10 states right now where if you take the same case study and put it in that state, the electrification option makes more sense right now. And that's only going to continue to grow. But right now, I see more push for vacuum coming from process flexibility, process results, quality, safety, and insurability than necessarily just emissions.
Good. Right. Well, if anybody else has a question for Brian, while we have him here, please type that into the Q&A panel there. But his information, contact information is up on the screen. So feel free to reach out to him if you have something else when this ends. And again, we will be sending out a link to the recording once that's processed. So you'll be able to access all of this information again to view and listen and jot down some more notes. Brian, if you don't mind just flipping to the next slide there, and we'll just remind everybody to watch for the details on our second summit that is geared toward the sustainability and decarbonization initiatives we're doing here at IHEA. And if that's it, then I want to just thank everybody for their attention, and please be sure to give us your feedback. Watch for that email link, and we appreciate your attention today. Have a great rest of your afternoon. Thank you,
Thank
everyone.
you. Take care.
Thanks, Brian.
Thanks, Kelly.
Bye-bye.